Alright, everybody. I'd like to welcome you to 14.2 Wave Properties. And I wanted to start out watching this video. I saw this video when I lived in Hawaii, and there are very few videos that would give me goosebumps watching it, and this was one of them. You probably won't be able to hear the sound, but that's okay. I wanted to show you that because waves are amazing. They're just incredible entities. And where do they come from? Like ocean waves, they come from storms that have high pressure systems that have pushed waves across entire oceans, and they end up landing on the shore. And that was a video of Mike Parsons on the north shore of Maui at a place called Jaws, and it was a 50-foot wave that he just surfed. A wave is a rhythmic disturbance that carries energy through matter or space. Medium is the stuff a wave goes through. So that's the matter or space. That's what a medium is, the stuff that waves travel through. A wave pulse is just a single bump that you can see below. I've got a little animation down here that shows just a single bump. That's a wave pulse. Periodic waves are bumps sent at regular intervals. So disturbances at regular intervals. Now, there are three kind of main types of waves. The first type is called a transverse wave. And here's an example of a transverse wave. You've probably all been a part of something like this. A transverse wave is when the medium vibrates up and down. People are vibrating up and down, but the wave travels left and right. So we've got an up and down motion, left and right. That's what a transverse wave is. So it's the medium vibrates perpendicular to wave direction. A longitudinal wave is where the medium vibrates parallel to the wave direction. You'll notice that this is a sound wave. This is what happens with sound, is you've got particles that are pushed and that they run into each other like a Newton's cradle. These particles are vibrating left and right as the wave travels to the right. So this is called a longitudinal wave. Medium vibrates parallel to wave direction. Now, there is one other type of wave, and it's called a combination wave. And this is what water waves are. This is an example, an animation I pulled off online. Now, if you've ever been in the ocean, you'll notice that as a wave comes in, you're making like a circular motion. Like you're going back and forth, up and down. So you're not vibrating strictly left and right, nor are you vibrating strictly up and down. You're vibrating both ways, both up and down and left and right. And this is what a water wave is. It's called a combination wave. Now, there's a couple ways that we measure waves. Waves can be measured as they're traveling across. I was just on NOAA's website, the National Oceanographic Atmospheric Administration, and they had a pretty interesting animation, if I can quick find it. Here's just a wave bobbing up and down, and we have ways of measuring waves. We measure their amplitude, we measure their speed, we measure their what's called wavelength, we measure what's called their frequency. And this is just a buoy. As the waves are traveling underneath it, these buoys that we have, there's a system of them all around the continental United States that protect us from they don't protect us, but they warn us of tsunamis. They can forecast the surf. So if you lived on the coast, they would actually tell you the surf forecast for the day. So this is kind of an animation that shows waves going up and down. And let me tell you and show you how we measure them. Now, the first thing is the speed. And you saw it there. It's how fast the wave is going laterally. So like, how fast wave is moving through the medium. How fast it's moving through the medium. The amplitude is how tall it is. If you look down here, you'll see that I've got a wave. This distance from here to here, we call it the amplitude. And we measure how tall the amplitude is in meters. And you could do it a couple of ways. This is the peak to peak amplitude sometimes, or we can do peak to like the center. So you have to kind of be careful when they talk about amplitude. Are they talking about from the middle to the top, or are they talking about from peak to peak? The wavelength, that's how far a wave is. How far from crest to crest. So this right here, this distance from here to here, this is the wavelength, the length of a wave. We measure it also in meters. The period. The period is how long it takes a wave to repeat. And we measure that in seconds. So this one right here, we kind of call this one, it's seconds per wave. How many seconds is it for one wave? Now frequency, on the other hand, frequency is the exact opposite. It's how many waves per second. How frequent, how many waves pass in 1 second. So this one is different because it's waves per second. And the units that we use for frequency are hertz, Hz, that's abbreviated, Hertz. So 1 hertz is 1 wave per second. Now you're going to see some of these words in equations. For instance, you'll see speed and it will be denoted with the letter V. Amplitude you'll see with the capital letter A. Wavelength you'll see with a Greek letter that looks like an upside down Y. That Greek letter is called lambda. Period, we use a capital T, and frequency we use an F. Now there are a couple of equations that we use inside of waves. Just like there we have velocity equals distance over time with things, wave velocity, the distance of a wave, also known as a wavelength, the time it takes is period. So there's a way to find velocity of a wave, and that's wavelength make sure it's in meters, divided by period. Make sure it's in seconds. And then you'll get meters per second. And there is a way where period is related to frequency. So if you've got the frequency, it's 1 over the period, and vice versa. Period is 1 over the frequency. Remember how we talked about just a second ago? This one was seconds per wave, and this is waves per second. They're reciprocals of one another. So if you've got the period, you can understand the frequency. You just take one divided by the other one. Now here's an example problem from your book. It says characteristics. A sound wave's got a frequency of this. It travels a length of a football field in this many seconds. So we've got a lot of stuff. We've got frequency, distance, time, bam. So part A says what's the speed? Distance divided by time. So you take the distance it travels divided by the time. You can find the speed. And that comes out to be, pull out my calculator, 337. Part B, what's the wavelength of the wave? Well, remember that, let's see here, velocity is a wavelength divided by period, or we can also say wavelength times frequency. So we could use that one. We now know the velocity, and I'm just substituting in 1 over t for f, so the wavelength I'm looking for, and the frequency is 192. So I take 337 divided by 192, and my wavelength comes out to be 1.76 meters. Part C, what is the period of the wave? Remember the period is 1 over the frequency. So we have the frequency up above, which is 192. So you take 1 divided by 192, and you get 0.00521. Now that's seconds. Now that's crazy. It takes 5 milliseconds, or 5 thousandths of a second, for a wave to repeat itself. And that's not uncommon for, that's actually pretty slow in terms of sound waves. So sound waves vibrate actually really, really quick. And we'll do some more experimenting with that when we talk about sound next chapter. And then letter D. If the frequency was changed to 442, what is the new wavelength? So when you speak, you know, waves travel out. So now we make it more frequent. So we start vibrating it. So my guess is the wavelength is going to go down. So let's see. Frequency 442, what's the new wavelength? So we'll go like this. Velocity equals wavelength times frequency. It still goes the same distance in the same amount of time. So I'm still going to go 337. The frequency goes to 442. So find the new wavelength. So you take 337 divided by 442. And you get 0.762. Oops. Oh no. And it also wants to know what is the new period. And then the period is going to be 1 over the frequency. So I take 1 divided by 442, my new period, and that comes out to be 0.00226. Now this only has 3 significant figures, remember. So it's all good. Alright, that's what we've got on wave properties.